Welcome to Computer Science. In this first learning outcome, we get to grips with hardware, the physical parts of a computer you can actually see and touch. And we look at how those parts shape what a machine can do and how you would pick the right one. So, what do we actually mean by hardware? Think of everything in a computer you could pick up and hold: the chips, the boards, the drives. That is the hardware. And it works hand in hand with the software, the programs, to take data in, process it, store it, and push results back out. Most laptops and desktops follow what is called the von Neumann model: a processor, some memory, and input and output, all linked together. Across this outcome, we will name the main parts, but more importantly, understand what each one is actually for. Let us open the lid on that von Neumann design. At the heart sits the processor, or CPU, and inside it are two teams: the control unit, which fetches and decodes each instruction, and the arithmetic logic unit, which does the actual sums and logical decisions. Alongside it, RAM holds whatever instructions and data are in use right now, while input and output devices shuttle information in and out, all connected by the system bus. The clever idea here is that the program and its data share the very same memory, which is why we call it a stored program computer. A few components form the backbone of any machine. The CPU is the brain that fetches, decodes, and executes instructions, something like an Intel Core i7 or an AMD Ryzen chip. The motherboard is the big circuit board everything plugs into, letting the parts talk to one another, and the power supply, the PSU, converts the mains electricity from the wall into the low-voltage direct current the delicate components actually need. What makes one processor faster than another? Three things mostly. Clock speed, measured in gigahertz, is how many cycles it races through each second. Cores are like having several workers, so a quad-core or 8-core chip juggles many jobs at once. And cache is a little pocket of ultra-fast memory right on the chip for the data it reaches for most. For example, a Core i5 at 3.6 GHz suits everyday office work, while a Ryzen 9 at 4.5 GHz with 12 cores is built for something demanding like video editing. The catch is that more speed means more heat, so fast chips need serious cooling. It helps to keep three kinds of memory straight. RAM is your fast-working memory, but it is volatile, so the moment the power goes off, whatever was in it simply vanishes. ROM is read-only and non-volatile, quietly holding the startup instructions even when the machine is switched off. And cache is that tiny, blazingly fast memory tucked inside the CPU, storing what it thinks it will need next. Memory is arranged as a hierarchy, and it is a neat trade-off between speed, size, and cost. Right at the top sit the registers and cache inside the CPU, tiny but lightning quick. Below them, RAM, larger and fast but volatile. And at the bottom, the secondary storage, huge but slower. Data climbs up the hierarchy when it is needed and drifts back down when it is not. Picture a chef's kitchen. The ingredients on the worktop are grabbed instantly, the pantry holds more but takes a walk, and the cold store out the back holds everything but is slowest to reach. Let us talk about how it all wakes up and connects. The BIOS is firmware living on the motherboard, and it is the first thing to run when you press the power button, checking the hardware and loading the operating system. Adapters and controllers manage how your drives plug in, using standards with names like SATA, eSATA, and the older IDE. Those old IDE drives shared one cable in a master and slave arrangement, whereas modern SATA gives each drive its own private connection, which is tidier and quicker. Ports and connectors are simply the doorways data uses to get in and out. SATA and eSATA handle your internal and external drives, while the older IDE connected legacy hard disks and optical drives. Then there is the familiar USB port for keyboards, mice, flash drives and printers, And a couple of veterans, the serial port that sends one bit at a time, and the parallel port that pushed several bits side by side, once common on old printers. Some parts add extra abilities or keep things running safely. Expansion cards slot in to give new powers, a graphics card to render images, or a network card to get online. Cooling keeps everything within safe temperatures, usually a fan and heat sink sitting on the processor, plus a few case fans moving air through. And of course the hard drive, or SSD, provides the permanent storage that survives a power off. If the cooling ever fails, the CPU will deliberately slow itself down or shut off completely rather than cook itself. Here is a question students often get wrong. Which single part makes a computer fast? The honest answer is none of them on its own. Performance comes from how the CPU, the RAM, the storage, and the graphics all work together, and a brilliant processor starved of memory or stuck with a slow hard drive becomes a bottleneck. The way we judge a system is to read its specification sheet and ask whether it matches the job it is meant to do. Let us put two machines next to each other. System A has a 4-core CPU at 3.6 GHz, 8 GB of RAM, a 500 GB SSD and built-in graphics. System B has an 8-core chip at 4.2 GHz, 16 GB of RAM, a 1 TB SSD and a dedicated graphics card, so System B has roughly double the cores, memory and storage plus a far stronger graphics processor. For browsing and writing documents, honestly both are perfectly fine, but for video editing System B pulls clearly ahead. Now let us actually make a decision with those two systems. Imagine an accountant who needs a machine for spreadsheets and email, and a designer who needs one for 3D rendering. The accountant's work is light, so System A's 4 cores, 8 GB and speedy SSD load a spreadsheet and email instantly, and it is cheaper, so it wins. 3D rendering, on the other hand, leans hard on the processor and graphics, so System B's 8 cores, 16 GB and dedicated graphics card slash the render times. The lesson is to match the specification to the workload, because buying System B for the accountant wastes money, and giving the designer System A just leaves them frustrated. When a real organization buys computers, cost is only the start of it. There is the budget and running costs, of course, but also compatibility. Will the parts actually fit the motherboard and work with what you already own? You weigh performance against genuine user needs, enough speed but no more, then security, reliability and support, things like warranty and updates. And finally, whether you can even get hold of it and set it up in the time you have. It is worth turning those factors into questions you can actually ask. On cost, does it fit the budget, like a school buying a class set of mid-range machines? On compatibility, will the new RAM match the motherboard type? On performance, is it fast enough? So video editing would demand a strong graphics card. On security, can sensitive data be encrypted? And on usability, is it right for the person? Perhaps an accessible keyboard for a user with a disability. Let us ground that in a real choice. A design studio of 6 staff is replacing all its computers on a fixed budget, because the team runs graphics software, RAM, and a dedicated graphics card matter most, and the new machines have to work with the studio's existing monitors and network printer. Buying 6 mid-range workstations keeps everyone productive, which is far wiser than splurging on 2 top-end machines and leaving 4 people struggling. Add a 3-year warranty and automatic backups, and you have balanced performance against budget across the whole team, rather than chasing one perfect machine. Peripherals are all the devices you connect that are not part of the core system. Input devices send data in, your keyboard, mouse, scanner, camera, touchscreen, or microphone. Output devices send results out, the monitor, printer, plotter, speakers, even a VR headset. And accessibility devices open the machine up to users with additional needs, things like large key keyboards, screen readers, eye tracking, and switch controls. Choosing a peripheral really comes down to the job in front of you. Printing photos. An inkjet blends colors beautifully. High-volume office printing. A laser is fast, sharp, and cheap per page. Big architectural drawings call for a plotter. A public information point wants a robust touchscreen with no fiddly mouse. And a user with limited vision is served by a screen reader paired with a large key keyboard. Same idea, but the right tool shifts with the situation. Picture a school reception that has to sign visitors in, print badges, and be usable by staff with different needs. A touchscreen lets a visitor sign in quickly with no training at all. A label printer runs off a badge on demand, and a webcam grabs a photo for that badge and the day's record. Then an adjustable large key keyboard and a screen reader make the desk workable for every member of staff. Notice that each choice is justified by the task and the people, not simply by which is cheapest. There is no shortage of ways to back up your data, each with its own personality. Magnetic hard drives give you huge capacity for very little money, but they have got moving parts and are slower. Solid-state drives are fast and tough with no moving parts, though they cost more per gigabyte. Flash and USB drives are wonderfully portable, but easy to lose or damage. Optical discs like DVDs are cheap and stable, but small and slow. And cloud storage lives off-site and is reachable anywhere, as long as you have got internet and trust the provider. Line those up against what you care about and the picture sharpens. A magnetic hard drive offers enormous capacity, into the terabytes, but it is bulky and stays local. An SSD gives high capacity and real speed and can be encrypted. A USB flash drive is supremely portable but easily lost, so encrypt it. Optical discs come in read-only forms that resist tampering, while cloud storage lets you reach your files anywhere. But its safety rests on the provider and your password. So which backup is best? The honest answer is that there is not one. It depends on capacity, speed, portability, security, and cost. For fast-working storage, an SSD wins. For cheap bulk backup, a magnetic hard drive is hard to beat. And for protection against fire or theft, cloud backup is strong, though it leans on your internet and a trusted provider. Good practice follows the 3-2-1 rule, 3 copies of your data on 2 different types of media, with 1 kept off-site. Evaluating, remember, means weighing those trade-offs and recommending a sensible mix, not crowning a single winner. Let us draw this outcome together. Hardware is the physical side of a computer, and the von Neumann model ties the processor, memory, and input-output together through buses. Processor performance rests on clock speed, cores, and cache, while memory forms a hierarchy from registers and cache down to RAM and secondary storage. Assessing a system means reading its specification and matching the CPU, RAM, storage, and graphics to the task, and every real choice balances cost, compatibility, performance, security, and the user's needs. Finally, peripherals are picked to suit the situation, and backup storage is evaluated against capacity, portability, security, and cost. That brings us to the end of Learning Outcome 1, where we have travelled from the physical components inside a computer right through to judging whole systems, choosing peripherals, and evaluating backup storage. If you would like to go further, the reading list points you to solid textbooks on computer organisation by writers like Patterson and Hennessy, along with hands-on sites such as PC Part Picker and Tom's Hardware, where you can compare real components. There is also reliability data from Backblaze comparing hard drives and SSDs in the field, which is genuinely eye-opening. Do dip into those, and remember, the assessment wants you to explain what components do, not just name them.